welcome to this session. In our session today, we'll talk about the equidimensional equations, also known as the Cauchy Euler equation. A Cauchy Euler equation, or the Euler-Cauchy equation, or also known as the equidimensional equation, is a differential equation that will take this form: a naught x raised to power n times the nth derivative of y, then a1 times x raised to power n minus 1 times the nth minus 1 derivative of y with respect to x, and so on up to a and y, so that each term can be expressed as ak times x raised to power k times the kth derivative of y with respect to x, k taking the values from 0 to 1, 2, 3, all the way up to n. K is a positive integer or a natural number. Now, ak here, which represents a naught, a 1, a 2, all the way up to n, are constants. So, in this course, we shall consider the special case where n is 2, so that our differential equation will reduce to a second order ordinary differential equation of the form a naught times x squared times the second derivative of y with respect to x times a1 times x raised to power 1 dy dx, then plus a2. This one will be a2, this one here. This one here will be a2 y raised to power 1. So in this case, we shall consider a second order differential equation of this kind, so which is an equidimensional equation of order 2. So by the end of this session, you should be able to identify an equidimensional equation, what we are calling the Cauchy Euler. And we shall use a transformation to transform this into a second order differential equation with constant coefficients. So we should be able to transform this into that and then solve the resulting differential equation. So as we have said, an equidimensional equation, also known as the Cauchy Euler equation, or sometimes the Euler-Cauchy equation, is a second order differential equation that will take this form. So here a, b, and c are constants. So now, if f of x is 0, if f of x is identically 0, then the equation will be said to be a homogeneous differential equation. Otherwise, if f of x is non-zero, then the equation is non-homogeneous. And we have a theorem here that the transformation x, which is equals to exponential z, will reduce the equidimensional equation to a second order differential equation with constant coefficient. So this is the transformation we shall be using when we want to solve this differential equation. So we shall write x is equals to e raised to power z, or even z is equals to logarithm of x, so that we can differentiate z with respect to x. We can differentiate z with respect to x, or even we can differentiate from here x with respect to z. Whichever way we do it, we should end up with the same result. So we shall start with x is equals to e raised to power z, and then say that if we differentiate x with respect to z, then we get the same expression, e raised to power z, which is basically equals to x. So that dz by dx is equals to x. Now, because we are going to use the transformation, we want to transform this differential equation and replace the variables x with z. So then we shall do the transformation of the differential coefficients appearing in the differential equation. So we see that we have dy dx, but we want to express this in terms of z. We also have d squared y by dx squared. We want to express this in terms of the variable z. So we make use of the chain rule that if we have dy dx and we want to introduce a variable z, then we can express this as dy dz and then multiply by dz dx. This is known as the chain rule in the differentiation. So see that now from here we have dx dz here. So if we want dz by dx, this is the reciprocal 1 divided by dx by dz. And because we have seen dx by dz here is equals to x, then we can replace and get dz by dx is equals to 1 over x as we have here in this expression. So we want to substitute back dz dx. We see that we have dz dx here, which we can now write 1 over x. So we replace this with 1 over x. So what we get is that we were having dy, see that we have dy by dx is equals to dy by dz times dz by dx. But now dz dx we replace with 1 over x so that we get dy by dz times 1 over x. So in this case, dy dx is equals to dy dz times 1 over x. Or we can write this one as 1 over x dy by dz. So dy dx is equals to 1 over x dy by dz. So we are going to call this equation 1, as we have here. Then now the second order derivative. The second order derivative. If we have the first order derivative, then to find the second order derivative, we just need to differentiate that. So we have dy dx. We want to find d squared y by dx squared. It means that we differentiate dy dx with respect to x. So we write d by dx of dy dx. But dy dx here is given by 1 over x times dy dz. So we substitute here 1 over x dy dz. Now we see that we need to differentiate this quantity, which is a product of two quantities. Remember, when we are differentiating a product, the derivative with respect to x of u times v is usually given by u times dv by dx plus v times du by dx. We call this the product rule of differentiation. So because we have a product here, see that now we can set our u to be 1 over x and v to be dy by dz. So if we do that, then we see that the first term here, which is u dv dx, becomes u is 1 over x here. So this one becomes 1 over x times the derivative with respect to x of v, which is dy dz. The second term, which is v times du dx, becomes v, which is dy dz, times the derivative of u, the derivative of 1 over x with respect to x. So we have this term here, u dv dx is this term here. And then the next term, which is this one, is the derivative of u, this is u, times v, this is v, dy dz. So we differentiate these terms. So see that now when we want to differentiate u, what we are calling du by dx is equals to the derivative with respect to x of 1 over x, which we write the derivative with respect to x of x to the power minus 1, and this is minus 1 or minus x raised to the power minus 2, which is minus 1 over x raised to the power of 2. So the derivative of u with respect to x becomes that. Then the derivative of v, when we write this dv by dx, this is the same as d by dx, and our v is dy by dz. Remember, v here is dy dz. Now dy dz, now this one is a function of z. So a function of z cannot be differentiated directly with respect to x. What we can do is that we can apply the chain rule. So it means that we can apply the chain rule. So we first differentiate this function with respect to z, and then because we want to have our dx, so it means that we multiply by dz by dx. Notice that here, this one is not different from what we have here, because if we can cancel out dz with dz here, then you'll have d by dx. Now, but we are not going to cancel out because we want to evaluate this. So now this one becomes, see that this quantity inside the brackets here now becomes d squared y by dz squared. dz by dx, we know what is dz by dx from up here. We had done that. dz by dx, we know it is 1 over x. So this means that we can substitute. So we get this is 1 all over x. So now, what do we want to have? We want to write the, remember we had du times v by dx, the product. We had v du by dx plus u dv by dx. Notice that it doesn't matter which term you are starting with, because this one is a sum. You can start with this term, or you can interchange the terms here. So then what is our v? V is v here is dy by dz. du dx, we have du dx here is this minus 1 over x squared. So we can write minus 1 all over x squared. U is 1 over x. dv dx, we have seen here, this expression here is 1 all over x d squared y by dz squared. So that see that we can now open the brackets in the second term, and we get 1 over x times 1 over x, so which is 1 over x squared. And then we can factor out, we say we have 1 over x squared in the first term and 1 over x squared in the second term. So when we simplify that, we can factor out the 1 over x squared, and we get this equation, which we are going to call equation 2. So now, by substituting in our equation, the expression x is equals to e raised to power z, because this is the transformation that we shall be using. The first derivative becomes this. The first derivative becomes this expression here. The first derivative becomes this expression here, which we are calling equation 1. While the second derivative will be the equation 2 here. So these are the two equations that we shall need when we are solving the differential equation of this kind. So in this case, let's do an example. You are given a homogeneous second order differential equation, which is an equidimensional. You can say the term x squared and d squared y by dx squared and x dy dx. So we are going to choose the transformation x is equals to e raised to power z. And once we have this transformation, the first derivative becomes that, the second derivative becomes that. So where we have the first derivative here, we shall write 1 over x dy dz. Where we have the second derivative, we shall have 1 over x squared d squared y by dz squared minus dy dz. So then everything else will be retained as it is. So we start with x squared. See that we are going to start with x squared. Then we put this quantity. That quantity is 1 over x squared d squared y by dx squared minus dy. Oh, sorry, this is not dx, but dz minus dy by dz. That will be our first term. The second term, we have minus 2x here. Minus 2x, then dy dz, we substitute this expression, which is 1 over x dy by dz. The third term is just 2y. There we are not substituting if anything, then it's equals to 0. So this is the expression we have. Notice that the x squared here cancels this one, and x cancels x here. So that the first term here, we are left with this, which is d squared y by dz squared minus dy by dz. The second term, when we cancel out x, we are left with minus 2 dy by dz. The third term is 2y, and the other side we have 0. So that now we can add the right terms. So you see the two middle terms here, the second and the third term can be added to get minus 3 dy dz. So our differential equation becomes d squared y by dz squared minus 3 dy dz plus 2y is equals to 0. And this one is a second order ODE with constant coefficient 2. And notice that this differential equation is homogeneous. So to solve this differential equation, we just need to get the characteristic equation, solve the characteristic equation, and then we can write the general solution. The characteristic equation we have lambda squared minus 3 lambda plus 2. This is a quadratic equation. The roots will be given by minus b plus or minus the square root of b squared minus 4ac divided by 2a. And notice that a is the coefficient of lambda squared is 1, b is the coefficient of lambda is minus 3, and c is the constant term, which is 2. So by substituting these values, we see that b is minus 3, so minus b is 3, plus or minus b squared will be 9, then 4 times 1 times 2 is 8. So we get 9 minus 8 is 1. So the square root of 1 is 1. So we get the 2 roots. Lambda 1, which is 3 plus 1 over 2, that's a value of 2. And lambda 2 is 3 minus 1 over 2, a value of 1. We note that the roots of the characteristic equations are real and distinct, so that we can write the general solution to be of the form C1 e raised to power lambda 1 z plus C2 e raised to power lambda 2 z. Notice that our variable here is not x. Our variable in this differential equation, our independent variable in this case is z and not x. So we're going to write e raised to power lambda 1 z plus C2 e raised to power lambda 2 z. So this is the general solution. So lambda 1 is 2 and lambda 2 is 1. Lambda 1 is 2 and lambda 2 is 1. So we can now substitute these values. Lambda 1 is 2, lambda 2 is 1. When we substitute, we get C1 e raised to power 2z plus C2 e raised to power z. But remember, e raised to power z was x. So when we write e raised to power 2z, which we can write e raised to power z raised to the power of 2, this will be x raised to power 2. So that we can now substitute back. Where we have e raised to power 2z, then we get x squared. Where we have e raised to power z, we get x. And so we have C1 x squared plus C2 x. Now, similarly, we have another differential equation of the same kind. We can follow the same procedure. We set x is equals to e raised to power z. Then the first derivative becomes that, the second that. We substitute. Again, x squared cancels out here, and x cancels out here. The equation, the first term becomes d squared y by dz squared minus dy dz, as we have here. The next term, x cancels out here, and we have minus 3 dy dz. Then the last term is 4y. The middle terms here, these two terms, we can add them to get minus 4 dy dz, and then we get a second order differential equation with constant coefficients. We determine the characteristic equation, then we apply the formula to solve. Again, we have here the roots are equal. The roots are real and equal. If the roots of the characteristic equation are real and equal, then the solution is of the form C1 z plus C2 then e raised to power lambda z. Now, because our lambda is 2, then we shall get C1 z plus C2 e raised to power 2z. And remember now, again, here x is equals to e raised to power z, which implies that z is equals to logarithm of x by definition of logarithms. So in this case, we can substitute back. So where we have z here, we are going to put logarithm of x. And where we have e raised to power 2z, this becomes x squared. So that our general solution will be of this kind. So we have example 3. I will not go through that one, but you can get to solve this. The method is the same. We get the second order homogeneous differential equation with constant coefficients. The auxiliary equation is obtained there. Then the roots are complex. If the roots are complex, the general solution, if the roots lambda are complex, that is, are of the form alpha plus or minus I beta, the roots, or rather the solution of the differential equation is usually given by e raised to power alpha x or alpha z in this case, C1 cosine of beta z plus C2 sine of beta z. So this is how we write the roots. Now notice that in our case alpha is 0, beta is 3. So e raised to power 0 is 1. So we are not going to have that term. So we only have the quantity inside the brackets with beta is equals to 3. Then you can substitute back z is logarithm of x, and you get the general solution. Now, in this example 4, we have a non-homogeneous differential equation of the same type. So when we write x is equals to e raised to power z, then z becomes a logarithm of x. So notice that where we have the quantity on the right hand side here, x times logarithm of x, when we do the substitution, x becomes e raised to power z. So this term here will becomes x is e raised to power z, and logarithm of x is equals to z. So we are going to write z e raised to power z when we do the transformation. The first and the second order derivatives on the left hand side will be transformed the same way as we have done previously in previous examples. And the equation is reduced to a second order differential equation with constant coefficients. But notice that here the differential equation is not homogeneous because we have a term here. So the differential equation is a non-homogeneous differential equation. So when we have a non-homogeneous differential equation, we normally separate the solution y into two parts, yc and yp. Now yc is known as the complementary function, and yp is known as the particular integral. The complementary function is the general solutions to the corresponding homogeneous differential equation, while the particular integral is the particular solution to the non-homogeneous differential equation. The normal process is first to find the complementary function, then we can apply the method such as the operator to find the particular integral. So in this case, we need first to find the corresponding homogeneous differential equation, where we only replace the term here on the right hand side with 0. So we have a second order homogeneous differential equation. The solution to this will be known as the complementary function. And that one can be solved by first we obtain the characteristic equation. We solve the characteristic equation here, and we see that we get the case where the roots are equal. And if the roots are equal, we have said the solution will be C1z plus C2 e raised to power lambda z. So in our case here, z is 4. So we substitute. We get e raised to power 4z. And now, we can now apply the method such as the D operator method to find the particular integral. The particular integral, as we've said, is the solution, or is a particular solution to the non-homogeneous differential equation. So we write the non-homogeneous differential equation in terms of yp. Then we write this in operator form. Remember that d is the derivative with respect to x, which implies that when we write d squared by dx squared, then this one can be expressed as d squared, the square of the operator d. So where we have d by dz squared. Here we shall be using, because our variable is z, we shall not write x but z here and z here. So that we shall define d as d by dz and d squared as d squared by dz squared. So where we have d by dz, we shall write d. Where we have d squared by dz squared, we have d squared. Then here we don't have the derivative, so this one is just 16 yp. So we can factor out yp here to get d squared minus 8d plus 16, the whole of that multiplied by yp. Then we make yp the subject, so we can divide here. We don't normally divide by an operator, but we pre-operate with an inverse of the operator. But it will look like a division. But we have 1 over d squared minus 8d plus 16 operating on z e raised to power negative z. Now, here we shall use the theorems of the d operator. Theorem 2, which says that when a function of d operates on a function g of z times an exponential e raised to power kz, what you do is that you bring the exponential function forward, then the function, in the function of d is replaced with d plus k, and the new function now operates on g of z alone. So in our case here, the exponential function we have e raised to power z. So k is 1. And then g of z is equals to z. So we are considering the case where g of z here is equals to z. So we are having a function of d operating on z times e raised to power z. So k is 1. So we shall push the exponential function forward. Then in this function, we replace d with d plus 1, and the new function will now operate on z. So in this case, we have e raised to power z. So here we have d squared, d here in this expression, we replace with d plus 1. D plus 1, we simplify this. And we see that this reduces to d squared minus 6d plus 9. Operating on z. So we apply binomial theorem to this. See that when we have 1 over d squared minus 6d plus 9, we can write this one as d squared minus 6d plus 9 raised to power negative 1. And we can start with 9 plus d squared minus 6d and raise this to power negative 1. Notice that we can bring the 9 here forward. So we start with 9, then we add d squared and subtract 6d. So we're going to apply the binomial theorem. We are going to think of this as being of the form a plus b raised to power negative 1. So when we are expanding a plus b raised to power negative 1, the first term would be a, the next term would be minus 1 times a squared times b raised to power negative 1. The first term is remember when you have a plus b raised to power n, the first term is a raised to power n, the next term is n, a raised to power n minus 1 times b, the next term is n minus 1 divided by factorial 2, then we have a raised to power n minus 2 times b raised to power 2, and so on. So the terms are of that form. So in our case, we have 9 plus d squared minus 6d. This one raised to power negative 1. So the first term will be 9 raised to power negative 1. Then the second term would be minus 1. 9 raised to power minus 2. Then, because we are taking this, our first term here as our a, and the whole of this as our b. So then we have d squared minus 6d raised to power negative 1. So raised to power 1, sorry, not negative 1. So that the sum of the powers must always add up to negative 1. So we have minus 2 plus 1, which is minus 1, sorry. The next term would be minus 1 times minus 2 divided by 2 factorial, multiplying 9 raised to power minus 3 times d squared minus 6d raised to the power of 2. And the terms will be of that form, so that we get 1 over 9, and then we have minus, sorry, this is minus 1 over 81. Then we have d squared minus 6d. Now here we shall not need so many terms, because what we are differentiating is what we'll be differentiating is z. This one will be operating on z. Yeah, remember, this one will be operating on z. So when we differentiate z once, we get 1. We differentiate it the second time, we get a constant. We get 0, sorry. So in this case, by going to the third term has the lowest derivative, has the second derivative, considering that this one is a square. So we will not need that term. So we will not only be operating on this. So when we write yp is equals to e raised to power z, then we shall have this 1 over 9 minus 1 over 81. Then we have d squared minus 6d, and so on. This one operates on z. Notice that we can open the brackets here and get e raised to power z. So we can push the z inside here. So when it comes here, we get 1 over 9z, then minus 1 over 81. We have d squared z, and d squared z is 0, minus 6dz. And minus 6dz is, remember that dz is 1. Remember that when we write dz, we differentiate z with respect to z, we get 1. So d squared is the second derivative, which is 0. So in this case, this becomes e raised to power z. Then we have 1 over 9 times z minus 6 over 81 times 1. So that this is the particular integral. So once we have the particular integral, we can now substitute back. Remember the solution, y is equals to yc plus yp. We had obtained yc as c1 z plus c2 e raised to power 4z. And now we have yp as e raised to power z into 1 over 9 minus 1 over 9z minus 6 over 81. So that this will be the general solution. This will be our general solution. This will be our general solution. And in this case, we can then substitute back x is equals to e raised to power z. So where we have e raised to power z, like here, this becomes x. This becomes x raised to power 4. And where we have z, z is equals to logarithm of x. So we write logarithm of x here. and here. And that will be our general solution in terms of Z. So basically, this is the process of solving, and this is the process that we use to solve the equidimensional equation. There was some error here in this expression. So the correct expression is the one we have here. There was an error there somewhere in the expansion here. So don't look at that. The correct expansion should be, the binomial theorem is this one. Then we substitute a is equals to 9 and n is minus 1. So that becomes minus 9 raised to the power minus 1, which is 1 over 9. And 9 raised to the power minus 2, which is 1 over 81. So that correction should be made here as we have done here. So basically that's the process of solving the second order equidimensional equation. Now this PDF notes will be shared together with the video. So what we'll do is that when you open the video on YouTube, when you go to the YouTube channel and open the video, you'll see the video. When the video is playing, if you scroll down, and there will be a link here where we have some description. There will be a link to the PDF document. So when you click on the link, it should load the PDF notes, which you can read and listen to the video. So that will be shared together with the video on YouTube. So when you click, you just scroll. When you open the video, when it is playing, you scroll and you click on this link. You should get the PDF notes, which you can scroll to get to the bottom, or even download, or even save in your computer to read later. So basically this is the method that we call, these are the kind of equation, rather the differential equation that we call the Cauchy Euler equation. And basically to solve a Cauchy Euler equation, is very easy. All you need is the transformation. The transformation x is equals to e raised to power z. If you use that transformation, then dy dx becomes 1 over x dy dz. Then d squared y by dx squared becomes 1 over x squared d squared y by dz squared minus dy dz. You substitute those expressions, and the equation is reduced to a second order ordinary differential equation with constant coefficient. Then you can solve using the normal method that you have solved the other equation. Thank you, and you can go to your YouTube, as we have said, and download the PDF notes and then listen to the video as you go through the notes.